All right, guys, I just got kicked off for my next 15 minutes. Can't believe I'm going into a part 3. All right, let's make this short. All right, so I had just finished talking about, let's see, how ionic compounds are poor conductors in their solid form. Again, the reason why ionic compounds are poor conductors in their solid form is that rigid crystal structure, the positive-negative orientation of our ions in our crystal structure means that a negatively charged electron just can't wiggle its way through. Again, solids, they do vibrate slightly, but they're not going to really move that fixed position. So an electron is just going to get stuck in these pockets. It's going to be attracted to some positive cation, and then again, that cation is completely surrounded north, south, east, west, all directions with an anion with negatively charged ions, and then that electron is going to feel the rebuttal, the rebuffing of that negative charge, and is just not going to be able to move very well. Now, this is in comparison to our next bullet point. Ionic compounds are good conductors in their liquid form. So I want you guys on your guided notes, circle that word liquid. I do have a bullet point about it, but circle that word liquid. It's molten. So ionic compounds are good conductors in their molten form. So we said that ionic compounds are always solid at room temperature. In order to melt to a liquid or to sort of boil into a gas, you would need an incredible amount of energy. So we talked about how you would need thousands of degrees of heat in order to melt an ionic compound. So when we're talking about a liquid ionic compound, that's why we say molten, because it would be incredibly hot. So an issue here is if you want a conductor and you want to use an ionic compound, this is a huge safety risk, right? You're thousands of degrees. You're like looking at this molten salt, which, like lava, will destroy you. So when we are thinking about having ionic compounds as good conductors in their liquid form, they are good conductors because liquids move, they flow past each other. So too with the electrons. The electrons would be able to flow and slip past each other. But it's not a very good idea because then you would be working with something that is thousands of degrees hot. So this brings us to our next bullet point. Ionic compounds are also good conductors when they are soluble, when they are dissolved. So our next bullet point here says ionic compounds are usually soluble, which means they can dissolve. So to be soluble means you can dissolve. So you see this with your pasta water. So when you guys are making mac and cheese or spaghetti or something, you're boiling your water. Typically, you'll throw some salt in the water. When you put that salt in the water, it does two things. First and foremost, it helps your pasta not stick together. But more importantly, it is going to allow that water to boil faster. So ionic compounds, they dissolve and they have some properties that allow, for example, your water to boil a little bit faster. So ionic compounds are usually soluble, means they can be dissolved in water. That would mean that they would be good conductors. So salt water is a great conductor of electricity and heat. This is also why you are told to get out of the ocean if a thunderstorm is coming. So too with a pool. I would remind us though that even in a pool, it is a salt water. So freshwater pools, you could have a saltwater pool. My mom had a saltwater pool when she was growing up. But typically we have freshwater pools, but we're putting like chlorine, we're putting salts in them to regulate the pH and make sure that that water doesn't grow tons of bacteria and get all nasty. So they do have salts in them. So for the same reason, there are salts in that water, salts in the ocean, just more classic sodium chloride salts in our ocean. But that's why electricity travels really well through it. And you wouldn't want to be swimming during a thunderstorm. All right, last little bit here. Ionic compounds are hard and brittle. So last two blanks for properties, and then we'll define brittle and we'll be done. Ionic compounds are hard and brittle. So hard means the crystal's lattice is held together strong. Those forces of attraction between our cations and our anion, they're really strong. They require a lot of heat energy to be ripped apart. So we talked about how they have really, really high melting points and boiling points. However, despite being really, really strong and having these strong forces of attraction between cations and anions, ionic compounds are brittle. So we're going to use this term brittle. It's going to be the phrase or the kind of language that you'll hear, but let's define it. So what does brittle mean? Brittle means, we can just say something that could break or cleave or chip into smaller pieces or to fracture. If something is brittle, that means that it can break apart, it can cleave, it can chip into smaller pieces, it can fracture, it can break apart. Any of that type of language we'll use. I might ask you guys to describe it in your own words. So you might say something breaks apart or it chips down into smaller pieces, but mostly we'll be using this word brittle. So you see this with salt. Again, table salt is a great example. We have a lot of grain types. So if you think about like pink Himalayan rock salt, or maybe like a salt lamp, those are like gigantic pieces of salt. And then we have like maybe you guys have like a little like a pepper mill or a salt grinder, that kind of thing, where you have larger coarse pieces of salt that you can chip down into smaller pieces, smaller grains. If you only have like, thin, small pieces of like baking salt at your house, that originally was part of a larger piece of salt, but it's been chipped away into smaller pieces. And again, different reasons for different sizes. If you want to have, flakes of salt on your baked potato versus baking something to be evenly mixed in some cookies or something like that. But what we're saying here, the reason why we can have all these different grain sizes is because it's brittle. So the last thing here is I will be asking you guys a question about like, well, what happens? Describe to me on the atomic scale and on the kind of macro scale. So what we see with our eyes when we are smacking an ionic compound with a hammer. Eventually, we're going to compare this to metals. You guys may already know that metals like deform or dent versus these ionic compounds are going to chip or break apart because of their brittle nature. So these ionic compounds are super brittle because if we look back at our crystal structure, that plus minus alternation of charge, when you hit this charge here, when you smack the crystal lattice with a hammer, it's going to cause the entire plane to shift. So instead of having a positive negative attraction, then you'll have a negative negative attraction or a positive positive attraction. And at that very moment, when those atoms are shifted and the cations start to approach each other and the anions start to approach each other, immediately it will cleave, like immediately it will snap apart. That's what's happening, if you are breaking down salt, if you're grinding it into a smaller piece, you are chipping away at that crystal structure. You're breaking apart those ionic compounds. So I think that's it for today. I think those are all my notes. I'll have some review questions. I'll prep you guys on what our next lesson is going to be. And let me know how